Thanks for inviting me to Japan. It's my first time in Japan. I'm having a very nice time here. The workshop is also really nice. It's very nice to see so many people working on topics which are similar, yet there is something that's different, that I learned something from each one of the talks. It's going to be hard to follow Emmanuel's very nice talk. I'm going to try to do my best. But this is something like index coding, right? You know, he gave you one piece of information. Hopefully, I will be able to give you the other piece that gives you a 6 dB or whatever the improvement that we can get. So, as the big picture of the talk is this: interference is kind of the final frontier in wireless communications, right? Most wireless communication systems are interference limited, and recently there has been a lot of work in trying to deal with interference one way or the other. A new perspective for handling interference has been emerging in the last few years. And if I were to summarize this perspective, the perspective is to not think of interference as something that you need to get rid of, but to embrace or harness the interference. And the idea of lattice code seems to be very fundamental to this philosophy, and I'm going to try to give you a few examples. I'm going to start with giving you a few examples where this approach seems to make a lot of sense. So the first one is what's called physical layer networking, or compute and forward. And I'm going to give you 3 different examples. There are a lot of similarities between these examples, but there are also subtle differences. And these subtle differences are actually important in trying to understand which kind of coding schemes can be used for which one of them. So the main idea in physical layer network coding is to say the following: I have k users. Each person has some information. The important thing to note is that this information is typically over some finite field, and we do some encoding, and what we transmit in the end are n-length vectors, which are complex symbols. And there is a wireless channel, and what you receive at each one of the receivers is just a superposition of the transmitted signals. So we receive something like this. So the problem in physical layer network coding is for each one of these, you can think of these as relays, really. So the main idea here is to say that, well, if you are a relay, you don't really care about the messages of the individual users. You only care about computing some function of these messages, which you can forward downstream to a central destination, such that when the central destination gets all the information that's forwarded from these relays, it's able to recover the original messages. And one efficient way to do this is to realize that the channel gives you a linear combination over the complex field, and you try to choose some coefficients which are somehow close to these channel coefficients. So for example, one way to think about this is to say I'm going to find the closest integer to the channel coefficients, and then I'm going to try to decode the integer combination of the transmitted codewords. You will see why we want to do this integer combination in just a minute. This has to do with the fact that lattices are closed under integer addition. Okay. Now, in this particular problem, ultimately what we are interested in is in recovering this information bits. So one way to also think about this is to say that the receiver actually forms a linear combination over the finite field of the transmitted messages. You see, we have 2 different things. One is a linear combination of the x's. One is a linear combination of the w's. So this is over the finite field, whereas this is over the complex field. So this is the classic physical layer network coding or compute and forward problem. Okay? Now there's also a closely related problem which is called the integer forcing problem, or which can be thought of as a multi-user detection technique. So the idea is to say, well, these are all not really relays, but you can just think of them as different antennas at the same receiver. In which case there is no issue of forwarding things to a different destination. All of these things are simultaneously available for you in one place. So in this case, you don't necessarily care about decoding linear combinations over the finite field, as long as you can get enough information to be able to invert the linear combinations over the complex field, you are happy. But even though that's what you really want, it turns out that going to this finite field is still useful, and I'll try to convince you why this is useful. So the last thing I want to talk about is the interference channel. There's been a lot of interest in the interference channel. So in the interference channel, we have k users, and actually you can think of them as k receivers. Each person wants to send information to one receiver. So there is an intended user for each receiver, and then there is interference. And the idea is to say, if you look at any one user here, for example, there is a decide signal, there is interference, and then there is some noise. And the idea is to say, well, I'm going to try to first decode this interference directly. I'm not going to treat each one of them as a separate interferer. Somehow I'm going to treat the linear combination together as my interference, and if I can decode that, then I can subtract that out and then decode my decide signal. So again, here we don't necessarily care about doing any finite field linear combinations. We are happy with just decoding the linear combinations over the complex field. Okay. All right. So how do we really do this? I'm going to give you a kind of a high-level example of what goes on. So let's say we have two users, and so each user transmits a signal, and let's say we have channel gains, which are something like, let's say, 2.1 and 0.9. So the idea is each one of the encoders would encode their information with a lattice code. Okay. And the key point is that a lattice is closed under integer addition. Okay. So what might happen is this. Let's say user 1 transmits this signal, and user 2 transmits this signal. Now what I'm going to receive is this, 2.1 times this, which puts you somewhere here, plus 0.9 times this signal, which is going to put you somewhere over here, and then there's going to be some noise on top of that. So then a noise may put you somewhere around here. So the idea is to do the following. Well, 2.1 is somewhat close to 2, and 0.9 is somewhat close to 1. So what I'm going to do is I'm going to try to directly decode 2 times x1 plus x2. So 2 times x1 plus x2 is here, and since this is fairly close to what the channel gives me, I can decode this as long as the noise is small enough. And if you're happy with just recovering the linear combinations, we can leave it here. You got 2 times x1 plus x2. But if you really wanted to have if you have a relaying problem, so the problem in relaying is that 2 times x1 plus x2 has far more power than x1 or x2. What you can do is you can reduce it modulo the coarse lattice. You bring it here, and then you might transmit 2 times x1 plus x2 modulo a coarse lattice. And then if someone gave you x1, you can recover x2. Someone gave you x2, you can recover x1. So this is the main idea. So lattices have been around for a very long time, and they have been known to be optimal for the single user Gaussian channel, some side information problems. But really, in the last many years, we have realized that these are nearly optimal for a whole class of problems. There is the 3 problems that I just talked about. There is the index coding problem that Emmanuel talked about. There is secrecy. There is dirty multiple access. There is a whole bunch of problems, and this is why this is kind of exciting. Okay. So here's the question we are interested in. So how do we construct codes or lattices such that I can decode linear combinations? And when can I decode linear combinations over the finite field? Generally speaking, there are 2 approaches to this. One is to design the lattice directly in the Euclidean space. Brian has been doing a lot of work in this. This is called low density lattice codes. The other approach is to say I'm going to design lattices, but these lattices are based on some kinds of codes based on finite fields. This is the approach I'm going to talk about today. Okay? It's not actually entirely clear to me that which of the 2 approaches is better, to tell you the truth. I think this is still a bit of an open problem, and in fact, maybe a very nice paper to summarize the advantages and disadvantages of both these 2 constructions. But I will tell you, the spatially coupled LDLC codes are quite nice, and they actually perform fairly well. They are within a few tenths of a dB from theoretical limits. But what I see as being a little bit of a problem with this is there seems to be no systematic way to get close to these theoretical limits. And in fact, here is a quote from Brian's paper. It says that a significant open question is how to close this gap. I mean, it seems like still we don't really know how to design the LDLC code, and we don't really know how the Gaussian approximation works very well, right? So there are these two issues. So this is why we look at the second approach. And fundamentally what I'm interested in is this. What would be really nice for me is to make some statements similar to what we know for coding for the single user channel. So coding for the single user channel is a very mature field by now. We know how to get to capacity, we know how to get to capacity practically. So if there is a single user channel, what we would do now is to take the information, encode it with some kind of a binary linear code, use BICM or one of these modulation formats, and you have QAM. This kind of separation is optimal. This is the way to get close to capacity. We don't really use lattice codes to get close to capacity on the single user channel, right? So the question is there a similar architecture when you want to decode linear combinations? This is kind of what is in the back of my mind when I'm trying to look for these coding schemes. Now the problem we quickly see, and this is going to be a recurrent theme in my talk, is this. There is a bit of a problem when you try to use this kind of an approach directly for decoding linear combinations, and the problem has to do with the fact that the channel only gives you linear combinations over the complex field, whereas the code is really linear only over the finite field. There is this mismatch in some sense between where the addition takes place at the physical layer and where you really want linearity. The question is, when can we get linearity in the finite field when the channel only gives you linearity over the complex field? This is kind of a recurrent theme in the talk, and we're going to try to identify situations where this is possible so that we can build codes easily. Right? So particularly what becomes a problem is really this. If you just stick to binary codes and QAM, when you add QAM symbols over the complex field, this is not the same as doing modular 2 addition over the binary field. So our traditional things don't really directly work. Right? So to see what works, I need just a little bit of algebra. I must tell you, this is an engineering talk, and probably there are a lot of statements which are not precise. I'm not going to worry about that. I'm going to try to get the engineering intuition through. Okay, but there is a little bit that we need. So what we need, we're going to work with rings. So a ring is just a set with two operations, plus and multiplication, such that the ring is closed under addition, it has an inverse and an identity. Under multiplication, it is closed, it may not have an inverse, it may not have an identity. Although in this talk, almost everything that we're going to talk about has an identity. So a standard example of ring is the ring of integers. Also, the ring of integers modulo p. So if I look at the set, 0 to p minus 1, addition mod p, multiplication mod p is a ring. There are also going to be a few other rings that we will think about, and if you are not somebody who looks at these things on a daily basis, I think I was kind of excited to learn about these things when I started working on this. This is something that I think you may be excited to learn as well. So we have the ring of Gaussian integers. If you look at the set of all numbers of the form a plus b times I, this is a ring. Because when you multiply two complex numbers of this form, you also get another complex number of the same form. Right? Now, there's also the ring of Eisenstein integers, which is the set of numbers of the form a plus b times omega, where omega is a cubed root of unity. So if you take to the cubed root of unity, and again when you multiply two numbers of the form, you get another number of the same form. You add two numbers of this form, you get another number of the same form. So this is called the ring of Eisenstein integers. And more generally, we could do this is the most general thing we are going to work with. We have the ring of what are called imaginary quadratic integers. So the easiest thing is to think of numbers of the form a plus b times square root of d. We want d to be a square-free number, which means d is not divided by any perfect square. There are a few more constraints on this, but let's not worry too much about this. Numbers of this form. Okay, is that clear? Okay, so if you go back to ZP, if you go back to the set of numbers 0 to p minus 1, when p is prime, this becomes a field, right? So addition mod p and multiplication mod p along with this set gives you a field when p is prime, otherwise it's only a ring. All right. So now that we have just a little bit of algebra, we're going to try to first talk about what is pretty much the workhorse of all the proofs that I've seen in this area, which is called construction A. So what's the idea in construction A? The idea in construction A is actually pretty simple. We take some information, which is from a finite field. Think of P is prime. So we take information from a prime field. We encode it with the error correcting code. So I'm going to give you an example in 2 dimensions. So n is 2. I'm going to take 1 bit and encode it into 2. It seems trivial, but it's enough to make the point. So here's my generator matrix. It has 1 row, 1, 4 is the generator matrix. So there are 13 possible information bits. So 0, 0, 0 will result in 0, 0, 1 will result in 1, 4, 2, 8, 3, 12, so on and so forth. I get 13 numbers between the square 0 to 13 and 0 to 13. Right? So this is the set of all points that I obtain as the output of my code here. Now this by itself is not a lattice, but there's a very simple way to get a lattice from this. If you simply take this and you repeat it everywhere in R2, then you get a lattice. And this is what is denoted by this. So what this says is this: add integers of the form 13 times z. So you just take this block, shift it by 13 in every direction, then you are going to get a lattice. So one way to think about this lattice is this: any point which when reduced modulo p, so if I take this point and I reduce it modulo p, I will end up with something within this square, right? So for example, I will get this. If this is a valid code word of this code, then we say that this point is a valid lattice point. So that's the check to see whether something is a valid lattice point or not. Okay. All right. So what makes this construction a lattice? Well, what makes this a lattice is simply the fact that addition mod p over integers is the same as addition in the prime field where your code is designed. Right? That's really what makes this a lattice. So for example, if I take 2 lattice points like this and I add them up, I get something here. But the first point is a lattice of this form. I take a code word, I map it to integers, and then I add some multiple of 13. The second one is of the same form. So when I add both of them and then take modulo p, reduce it modulo p, all these terms go away. And I end up with m of c1 plus m of c2 mod p, but since addition mod p is the same as addition in the finite field, now I have another valid code word, and so this is what really makes this a lattice, right? Okay. Yeah, I think this just emphasizes this same point. Mathematically, as simple as this is, the core idea behind the more general constructions are already contained here. So what is really going on here is this. We have a ring, Z. Z is a ring. P times Z is an ideal. It's just a subset of the ring, right? Now there is what we call a coset decomposition. So what it means is Z can be formed as the union of PZ and many shifted versions of P times Z. So the ideal is given here. So if you look at all multiples of 13, I have 0, 13, negative 13, so on and so forth. This is 13 times Z. Now if I shift it by 1, I get all numbers such that the number mod 13 is 1, and then so on and so forth, and I can construct Z as the union of all these cosets. I take one representative from each coset, and then this forms what I'm going to call as a signal constellation. So this is nothing but 13 PAM, right? So one way to think about what we have done is simply this. I've taken a code over a finite field with 13 elements. I've simply used 13 PAM. And then I've added 13, some integer times 13 to construct my overall lattice. This is all we have really done so far. Okay, all right. So far now, what's the problem with construction A? Well, there is no problem with construction A if you want to do information theory, because it is known that if you pick that code over the linear field at random, then the resulting lattice is a very good lattice for almost everything you want to do. The real problem is in using this idea to design codes that are decodable and encodable with low complexity. So first of all, so there are a few restrictions. The first restriction I want to talk about is this. A lattice, as we have defined here, is closed only under integer linear combinations. So what that really means for our problem is that when the channel gives you linear combinations which are not integers, we are kind of quantizing the channel coefficients to the closest integer in some sense. So the question is this, can we quantize it to something else? It may be better for me to quantize it to something else instead of quantizing it to integers. Or equivalently, I'm asking the question, can I decode some other linear combinations of the transmitted signals instead of just integer linear combinations of the transmitted signals? That's number one. Number two is this. The information theoretic proofs to show that this construction A lattice is good all rely on the fact that the prime number in the prime field has to become very large. So essentially what is going on is this. A lattice looks like this, and in fact this is one of the problems of drawing the lattice in 2 dimensions. Really what is going on is this. As the dimensionality increases, the distance between the red dots is actually becoming larger and larger. But the distance between these green dots is always p, because if you think about it, there is one uncoded level on the top which is just adding 13 to whatever you transmitted, right? But this is completely independent of the dimension. If you want these two signals to be far away, then your p has to become really very large. So the question is, and then what's the problem with that? Well, the problem is now we are working with codes over very large fields, and the decoding complexity is pretty large. So the second problem is that can we somehow reduce this p? So these are 2 main problems with this construction A as it is. I'll skip the other one. So the main results in the talk I'm going to show are this. First, I'm going to show that we don't have to restrict ourselves to integer linear combinations. We can relax integer to an algebraic integer. Things like Eisenstein integers, I'm going to show that there are many integers that you can decode. So this lets you quantize the channel, not just to integers, but to other things, which improves the performance. This is the first result. The second result I'm going to show is that P does not actually have to become very large. We can take numbers which are not prime. We can take the prime factorization of the number, and it's enough for us to work with fields which are in the prime factors in the factorization. This is the Chinese remainder theorem that Emmanuel talked about. So for example, if you wanted to work with P is 210, there is no reason to work with a kind of ring of size 210. We can just build codes over F7 at most, and you can get the same effect of having decoded something with P being 210. And finally, I may not get to this because of the limited time. It turns out we don't even need construction A. Construction D is perfectly fine. It's a very nice way to get close to capacity. However, construction D is not sufficient if you really want to decode linear combinations of the transmitted signals. If you have forwarding problems, then construction D is not enough. If you want to do interference channels, or if you want to do integer forcing, this is okay. Otherwise, we still seem to need construction A.
What is construction A and construction D?
Okay, I'll get to it. Construction D is the same as what Hideki talked about this morning. It's a construction with multiple levels, where the codes in each level are nested in a code in the previous level. Okay, so we just need a little bit more of algebra. So remember we said the reason this construction A gave us a lattice is because of the property that addition over the real field modulo P is the same as addition over the finite field, right? So mathematically what this is nothing but this is a ring homomorphism. So if you think about the ring of integers and the ring of integers mod P, when P is prime, these are 2 different rings. But there is a mapping from one ring to the other which preserves operations. So there is a mapping which says that addition mod P, addition mod P with Z is the same as addition within the field, right? So this is really what we are looking for. What we are looking for is to say, okay, what are other structures where I can find similar homomorphism? So Z is only one ring, and P times Z is only one ideal, right? So the idea is to say, okay, I'm going to expand this and consider other rings, and we're going to look for prime numbers in these rings. And just like how 13 times z was an ideal which induced a coset decomposition of z, we're going to take the resulting ideal from this prime number, induce a coset decomposition, and I'm going to take the coset leaders from each one of them as my signal constellation. I have some pictures, I think it will make it clear when I show this. So that's pretty much the recipe. And there's a little bit of even more generality. The ideal does not have to be something that's generated by one element. In fact, this is something we recently realized. The most general result is that you will only need a prime ideal. You don't need it to be principal. Okay, so I'll give you some nice examples. Maybe in fact I can even skip this. I'll go to here. So the first example is from here. This is the ring of Gaussian integers. Right? So if you plot the ring of Gaussian integers, the ring of Gaussian integers is just like your QAM in right? So if you look at this complex number 2 plus 3 times I, this complex number is prime within this ring, which means you cannot take two Gaussian integers, multiply them, and get 2 plus 3 times I. Okay? So this is a prime number in this ring. Now what does that mean? Well, what that means is similar to how I constructed 13z, I can construct 2 plus 3 times I times z of I. So what I mean by that is this. You take 0, 2 plus 3 times I. So it's like scaling this whole lattice by 2 plus 3 times I. So this is what I've shown by all these red points here. Now, I can take these red points, I can shift these red points just how we shifted 13z to make all the integers by taking the set 13z and then shifting them by 1, 2, 3, so on and so forth. I can take all these red points, I can shift them by various values to create the entire lattice z of I. Right? This is what a coset decomposition is. And there is one coset, so for example, all the ones that are labeled 0 is the ideal. It is phi times z of I. Everything that's labeled 1 is just the ideal shifted by 1 to the right. Everything that's labeled 9 is just the ideal shifted 1 to the right and 1 to the top. Right? Okay. Now, why is this important? Well, what's really going on here is this. Because this is prime. Now, what I've really done here is this. I've taken a ring, I've taken a quotient with respect to a prime ideal. Just like how z slash 13z is the same as a field, is isomorphic to a field with 13 elements, this is also isomorphic to a field with 13 elements. And the point is, all we really need is a ring, and we need a prime ideal in the ring. So this number being prime is enough for us to create an ideal, and so this is isomorphic to F13. So what that means is this. If I take, let's take two numbers, 8, 9 and 8 for example. If I just add them over the complex field, if I take this signal, if I take this signal and I add them up together, I would get this, right? I get this. Now notice the labeling. The labeling is such that 8 plus 9 is 17. 17 mod 13 is 4. I exactly get a label of 4. So essentially what this says is this. There exists a labeling of these points such that when these points add in the complex field, the label that I get for the resulting point would be exactly the same label that I got by adding the labels over the prime field. So at the receiver, you can take what you receive, just reduce it modulo this region. This would be the equivalent of having added 8 and 9 over the prime field, so I can decode it with my linear code. Does that make sense? Now, so I want to give you another nice example, again with 13 elements, but from a different ring, right? So now I look at the ring of Eisenstein integers. So this is the blue points are all points which are of the form a plus b times omega. Omega is the cube root of unity, and this is actually called the hexagonal lattice in 2 dimensions. So what it says is I can pick a prime number here. I think 1 plus 2 times square root of 3i somewhere here is prime. Now I can do the same coset decomposition and I can label the points in such a way. For example, here you can take, if I take 1 and I add 10 to it, indeed I get 11. Right? So this is the way to get map labelings which has the required homomorphism for us. Now we can do it with other number fields too. So it seems like you have a whole variety of number fields that you can work with. And in each case, what you want to do is you want to look for a prime number in that ring, take the ideal generated by that prime number, take the Coset decomposition, you are guaranteed to get a mapping which has the required property. And look at this, I mean, this is actually a very nicely shaped constellation too, right? You get a slight gain over Gaussian integers even in terms of shaping, just in 2 dimensions. It's almost circular. In fact, the hexagon is the best you can do in 2 dimensions.
Krishna, you're 30 minutes in, by the way.
Okay, I still need about 10, I think. That's good. Okay, all right. Now come back to our the first question we asked, right? So finally, what does it mean for our architecture? Well, essentially, what this means is this: just like how you would the Coset leader as your signal constellation, just like how you use QAM or PAM, use this as your constellation and use this particular mapping that is generated by the Coset decomposition. And now you are all set. Anytime things add over here, I reduce it modulo this constellation, now I can decode the code. So we have used codes, everything from spatially coupled codes to show that these lattices get extremely close to the theoretical limit. You have a free reign to do whatever you want to do here. Any favorite code that you have here, you can put it here and then things work. Okay. All right. So let's skip this too. So I'll give you a little bit of simulation results to show why this helps. Suppose you have a 2 transmitter, 2 receiver case. The black is what you get by just doing what Nasser and Gaspar do, which essentially is the same as using just Gaussian integers. It's like saying I'm going to quantize the channel into integers. You can really see what happens at high SNR. High SNR, what happens is this: quantizing the channel to an integer starts to create a lot of self-interference. There's a little bit of quantization noise that you're not able to remove, right? If you go to Eisenstein integers, you can get a higher rate. I mean, this also has a problem. You know, ultimately, this also has some self-interference. You're also going to be limited by the self-interference, but nevertheless, you gain something. And one more result I want to show is this. So this technique, I think, is particularly useful when you have partial feedback. If somebody tells you a little bit about the channel, what you would do is this: you would pick the number field which gives you a closest approximation to that channel. You know, you have many number fields to work with. You have number fields of the form a plus b times square root of d, right? And d can be many different numbers. So you pick the number that gives you the closest approximation to the channel, and when you do that, you can get better performance over just fixing your fixing your modulation or the number field to be one of them. If you were to pick just one, the result says just pick the Eisenstein integers always. That's the best you are going to do because that quantizes the channel the best. But if you have partial feedback, I think then you can do slightly better. And I think we can use this with your phase precoding technique that Emmanuel has been working with also. Okay. And I think in the last one, I'm going to just very quickly go, and I'm thankful that Emmanuel already talked about the Chinese remainder theorem. I'll tell you where the Chinese remainder theorem comes in within the next 5 minutes or so. So essentially what happens is this, right? The Chinese remainder theorem gives you, so if you step back a little bit, what is it that we really required? What we really required was, I wanted a ring. We wanted 2 rings. One ring is the finite field. You wanted another ring such that there is a one-to-one map between these two. Now, one way to get a one-to-one map is through the Chinese remainder theorem. So the Chinese remainder theorem says the following. If my P is a product of many primes, then if I look at numbers of the form, suppose I have an integer x which is between 0 and p minus 1, if you know x mod p1, x mod p2 until x mod pl, then I can uniquely find what x is as long as x is between 0 and p minus 1. Or equivalently, what it means is this. Equivalently, what it means is, if you take, I'll give you an example. If you take the set 0 to 5, if you take 6 PAM, it means that I can label each one of these numbers by a vector of length 2, where the first element in the vector is from F2, a field with 2 elements, and the second element is from a field with 3 elements. And you get 2 and 3 because 6 is 2 times 3. In such a way that addition of these numbers modulo 6 will be the same as addition of their vector representations. Where for example, if I take 3 and 5, 3 plus 5 is 8, right? Now 3 is 1, 0, 5 is 1, 2. So I add 1, 0 and 1, 2. 1 plus 1 is 0 in F2 and 2 plus 0 is 2 in F3. So I should get 0, 2. And in fact I get 0, 2. That's really what the Chinese remainder theorem says. So now what this gives you is this gives you a homomorphism between the set of integers and some vectors, right? It is really a product of several rings. So I'll skip on. So what that really means is this. What I could do is I could do a multi-level construction now. So I would take my information, break it into many levels. So in the example, I would have the first level of information will be binary. It will be from F2. The second layer of information will be from F3. I would encode the first level with a code over F2. I would encode the second level with a code over F3. Now I get a vector. And then I map that vector onto a point between 0 and p minus 1. Now every user does the same thing. The channel gives you an addition over the complex numbers. But the Chinese remainder theorem tells me if you want to reduce it mod p, I can reduce each one of them, mod 2 first, mod 3 next, so on and so forth. So this becomes exactly a multi-level code. This is exactly Imai and Hirakawa or Wachsman and Huber in recent times, but the construction is exactly the same as that, except that the codes are all over different fields. Now the big advantage of this is that the complexity of decoding these is extremely small, right? I just take, like I showed you the example of 210, it's 2 times 3 times 5 times 7. I decode one code over F2, one code over F3, one code over F5, and one code over F7. But in effect, my P is really extremely large now. I think this is the main result here, and we can prove that these lattices are optimal. Just like how construction A gives you lattices that are optimal for coding, optimal for shaping, everything, we can show that these constructions are also optimal. For everything. This is the last thing I will do, but I think it's a pretty nice example, so I'll just give you an example and I will stop here. So let's see how we can use this for compute info, or actually the interference channel. So let's say I have a 3-user interference channel, and let's focus on what happens at the third receiver here. Say the third receiver receives, so the intended signal is this. At the third receiver, I want to decode H33 times X3, but I have interference. X1 was transmitted, the channel gain was 1. X2 was transmitted and the channel gain was 5. So I want to directly decode X1 plus 5 times X2, right? So I'm going to use this multi-level code. So here is what's going to happen. The first user, I'm going to assume that the code here is trivial. It's really no coding at all. It's uncoded. So the first user transmits the signal 2. This is the information from the first user. Now 2 in the vector representation is 0, 2. So we have 0 and 2 in the 2 levels. The second user transmits 1. 1 in the vector representation is 1, 1. So we have 1 and 1. Now the channel gain for the first user is 1, but 1 in vector representation is 1, 1. And the channel gain for the second user was 5, which in the vector representation is 1 and 2. So really what has happened is this. The process of forming H1 times X1 plus H2 times X2 is the same as taking this vector 1, 1, multiplying it component-wise with 0, 2. And then taking 1, 2, multiplying it component-wise with 1, 1, and then adding them both together. And that's exactly what happens when in the channel. The channel gives you 7 because it's 2 plus 5 is 7. But if you notice the label is 1, 1, which is exactly what you should get if you multiply this with this, multiply this with this, and then you add them up together. So what that really means is this. At the receiver, what you would do is this. You would first decode C1 plus C2. This is over the binary field. You would decode C1 plus 2 times C2 in the second level. So the 2 levels are actually decoding 2 different linear combinations, but each linear combination is within one of the fields, and this is equivalent to having decoded the linear combination 1 plus 5 times x1 plus 5 times x2. And this is exactly how we would do these things. And just like Emmanuel pointed, I mean, what I find to be beautiful about this, the power of algebra really is the generalization. It's easy for us to think about integers, but once you realize what's really going on is the Chinese remainder theorem and the homomorphism, now you can abstract it. Now instead of working with the integer ring, you can work with the Eisenstein integer ring. I have actually a nice example, but I don't have the time to show this. It works quite nicely in this. There are many extensions that I don't have the time for. One of them is to say, what if P is not a product of primes? Right? The Chinese remainder theorem works only when P is, well, really what it says is for any number you can look at the prime factorization, and the product of these rings is isomorphic to ZP. That's what it says. So it turns out you can build some constructions which can work in this case also. The one I showed you before works only when P is prime, but ultimately what seems to be important is this. There are two things that are important. One is a multi-level construction. You need many layers, one for each prime factor in your decomposition. If these prime factors do not turn out to be prime, rather power of a prime. So for example, if you take 12, 12 is 4 times 3. Well, this means I need a ring of size 4 and a ring of size 3. The ring of size 3 is the same as F3, but the ring of size 4 is not the same as F4. But it turns out you can construct the ring of size 4 as 2 levels of F2, but you will need the second level to be nested in the first level. So this becomes really more like the construction D. So the general construction has many levels. There is some levels of nesting depending on whether you get a prime or whether you get a power of a prime. That's really all that seems to be required to construct these lattices, to be able to decode linear combinations. Yeah, I think I'm way over time. If anybody's interested, I have some, I really wanted to say this too. This is a quote that I've used many times. I've been very inspired by Emmanuel's quote before. He did make a very interesting point. We're talking about primes, information coming from prime fields, right? It says, well, mathematicians like prime numbers, engineers like powers of 2. I'm certainly an engineer and I want to make a power of 2. And the way to make it work for a power of 2 is construction D. However, the problems are not solved because construction D will only let you decode the integer combination over the complex field. You cannot go back to the integer combination over the finite field. So this problem still remains unsolved. I'll finish up my slide with what I think are some important problems. Perhaps it may be valuable given that this is a project meeting. I still haven't seen a clean way to get the shaping gain, preserving the group structure. I think Brian was right. It seems like we are working on the right problems. Shaping, I think, is something that has not been done nicely. You can shape without, if you want to give up the quotient group structure, yes, you can do this. But then it's not clear that that is enough to decode integer linear combinations and reduce things, so on and so forth, right? I haven't seen a clean way to do the shaping, still preserving the quotient group structure. These multi-level codes are fine, but just like how multi-level coding is worse than BICM for finite length, we may have similar problems here also. This remains to be seen. The last problem I mentioned is this: construction D lets you decode integer linear combinations, but integer linear combinations are not enough for compute and forward. You have to reduce things. So for a classic example is this: if the channel gain is 2 for one of the user and 1 for the other user, you may end up getting x1 plus 2 times x2. But this 2 is really in a ring. 2 does not have an inverse in a ring. So even if I give you x1, you will never be able to find x2 because you did not get x1 plus 2x2 over a field, but you got x1 plus 2x2 over a ring. So I think this is an open problem too. So I think we'll stop here, and I'm sorry I went far over.
Okay, thank you, Krishna. That's very nice. So, do you guys have some questions?
I will start.
Okay, okay.
So, So Chinese reminder theorem works when you can take any co-prime numbers. They don't have to be just primes or powers of prime. Just that then your individual codes will be ugly, but
Actually, that is indeed a very good point.
so. And the other question is if you were able to design good codes over rings, maybe it would be all good.
Actually, this is a very good point, and I'll tell you something I found. So the reason I kind of shied away from this approach is I did not know much about codes over rings. And I had thought that we didn't know results like whether codes over rings are actually optimal for a symmetric channel. We know that codes over fields are optimal. It turns out in general codes over rings do not achieve the capacity of symmetric channels. However, it seems like codes over rings suffice to achieve capacity on the Gaussian channel. So this is in fact promising that you could actually build a code over a ring. But I have two comments to make about that. One is, there is a nice paper by Frank Shishang. Actually, one thing I did not do well is to clearly put many people have worked on this problem. I somehow was a little bit negligent to point out exactly who did what, but Frank did a lot of nice work on this. One thing they did show is, if you want to build a code over a ring, you can decompose it into nested codes over fields. So Z4, for example, you can build it as two codes, one over F2 and the other also over F2, but they are nested within each other. That's why I feel like finally all you require are codes over prime fields, but you may need nesting.
Yeah.
You had it?
And slightly different question. Do you see some use of lattices in non-coherent when you don't have, because radio gets faded. So do you see any role in lattices in
So
that
let's be a little bit clear to distinguish between fading and non-coherent, in the sense that, there is fading in whatever we are doing. It's just that the receiver can estimate the channel. That's the assumption.
Yeah.
So when you say non-coherent, you don't want the receiver to estimate the channel at all.
Yeah.
No, I have not. I have thought about this.
That's why I asked you.
It seems like an interesting problem. I haven't really.
Kind of hard because you can just look at amplitude, right? In non-coherent.
More questions?
I think during your talks, I think you said that the codes constructed by your scheme is optimal in some sense. So what kind of sense?
It's optimal. It achieves the qualitative limit. It also achieves AWGN channel capacity. So essentially the main results are this. So we construct a lattice. The lattice is good for coding, which means it achieves the qualitative limit. Now it is also possible to get a sequence of nested lattices which achieve the AWGN capacity. So which means if you take this lattice, there exists a sublattice, a coarse lattice within this sequence of lattices, which is good for shaping. So you can derive a sequence of lattice codes that achieve the AWGN channel capacity.
So regarding the AWGN capacity, so you also consider the power constraint?
Yeah. The difference between the qualitative limit and the AWGN channel capacity is the power constraint.
Is that similar type of argument where the Damir errors and Damir?
Yeah, it is actually very similar argument, and in fact, the proof to show that construction A work, it is good for coding. Actually, we find that the easier argument is based on Forney's work, very similar to construction D. We show that so the only thing you need to show is that the channel at each level has the required symmetry properties. and it's kind of clear to see that it does have that. To show that the lattice is good for shaping, we use the result by Oradenlich and Erez. There is a recent paper by Puri Erez and Oradenlich where they've cleaned up the proof to show that the lattice is good for shaping. Essentially what we do is this. You have this multi-level. At each level, you pick a subcode. And that's how you derive the shaping lattice. And this is enough to show that the shaping lattice, the resulting lattice is good for shaping. So this is big. Yeah, mostly these proofs are minor modifications of things that already exist.
So maybe you would have a proof for to answer the question he posed to me on index lattice code.
Yeah, in fact, I was going to say that when you said, you're right, I think this can be proved. I think this construction is optimal, is what I feel. Yeah, that's I was actually.
Thank you for answering.
Well, you know, we can guess and we can be wrong, but unless you have written something, it's not clear that it's correct.
No.
So.
Okay, more questions?
Yeah, I just want to make a couple of comments. I mean, there is a lot of interest in expanding these things to similar to what the other project is looking at in terms of random access. There is recent work on using compute and forward for random access, which seems, so essentially the idea is at each receiver you may get a different linear combination of the packets, which might let you decode different integer combinations of the same information.
Assuming some sort of block fading, or is two different
block fading.
receivers?
Block fading. No, two different time slots is what I mean. It's like, you know, you think of it, maybe two different receivers is fine.
Oh, yeah, I assume one receiver makes
If
it
you
very
receive one
interesting.
receiver, then you need different time slots.
Yeah, then you get, okay, it's interesting.
Yeah, I think.
So you mean each transmitter you should provide with some coefficient or some number? So then time slot 1 using different and time slot 2.
Yeah, you don't have to know this at the transmitter, right? So what you do is, you know, I think you had asked this question before too. So the issue, so let's say the transmitter just transmits. It picks a rate. This is where the difficulty is. Let's say I pick a rate and then I transmit. Now receiver 1 receives linear combination, right? It receives some h1 times x1 plus h2 times x2.
Yes.
I'm going to find some a1 and a2 and then I'm going to decode a1 times x1 plus a2 times x2. Receiver 2 may receive a different linear combination, so I pick a different linear combination to decode. Now if I forward both this information downstream, that may be enough for me to actually recover x1 and x2. You can rely on the randomness of the channel. However, the problem is, if you want to be able to decode a1 times x1 plus a2 times x2, your rate has to be such that you can decode from the worst of the two users.
Yes.
So if you can somehow overcome this, then I can see these things being used for random access, or you might layer information or something like that.
Thank you.
Any more questions for Krishna?
Actually, I want to ask in page number 29, you say that the skin comes for free.
Yeah. So I'll explain what I mean by that. The only difference between these two, so this is pretty much like using a prime-sized QAM constellation.
So both are using the image, complex.
Both are complex. You can think of this as complex QAM. So I think it's like, for example, 9 QAM or 13 QAM, but it's QAM. This is a hexagonal constellation. This is the constellation that you derive from Eisenstein integers.
This is the shaping game.
It's not only
No.
that's a very good point. That's a very good point.
Quantization.
It's not only the shaping gain. The real gain is the quantization gain in the channel. That's what I find to be interesting in these problems. Because, you know, when, like even Forney, way back when they talked about multi-level lattices, they make some comment saying, multi-level lattices are optimal. You can build these things over Eisenstein integers, but there's really no reason to build them over Eisenstein integers because you already know just using QAM is enough to get to capacity. But of course, they weren't thinking about quantizing the channels. And so this is really a quantization game, I think.
Do you think, I mean, do you think you could do a higher dimensional quantization and gain more or not?
No, I don't think you can gain because the channel is only a complex coefficient,
Yeah.
right? So even if you take 2 or 3 uses of the channel, if it's the same number, if the channel has not changed, the complex number is sitting only in the 2-dimensional space. You can't gain anything by going to a 3 or 4
No, multi-component, you could have a vector quantization.
Right, but if the channel stays constant over the, so if you go to, let's say, 2 uses of the channel, if the channel has not changed, essentially your channel only is lying on a line in the 2-dimensional, 4-dimensional space, right? So I don't think you will gain.
Okay.
If the channel has changed, you might gain, but then your lattice structure gets killed. So in fact, that's the other big open.
Fading.
So the biggest. So I'll maybe is it okay to just say 2 more things? So one of the questions that many people ask, including anybody who does self-introspection, is to say, okay, this seems very fragile, right? You want your channels to be exactly synchronized. You want your channels to not change at all. So it turns out that the synchronization is not really a big problem. We have some recent results which shows even if one of them is offset with respect to the other, you can get similar gains. But if the channel changes within a code word, this is trouble. So far I haven't seen solutions for this. I mean, minor variations is okay, but if there's fast fading, then I think you lose the algebraic structure.
For example, when you have an OFDM signal, then of course you have different channel coefficients on every subcarrier, and then you basically need to track the lattices for every subcarrier, right?
That's correct, but not only the tracking, even if you track them, when the channel changes, the sums of these things are not within the same lattice anymore.
Exactly, yeah. So you really have to construct for every
every
subcarrier
group of
basically,
subcarriers.
yes.
Or you have to code along subcarriers, which increases delay a lot. These are big open questions, I would say. But I find one thing to be nice is the fact that just from the modulation for perspective, you can gain something, right? It's like thinking of constructing modulation for physical layer network coding. You don't necessarily just have to do PAM. You can do lattices in small dimensions, which and the key thing is to make sure it interfaces correctly with your code in the end.
Okay, shall we finish? Let's thank Krishna. So let's take a 10-minute break now. We have a couple